Hi again. So yes, I think I've revived. I was flagging a bit during the last video. I have a couple of examples to do with non-conservative forces. And I wanted to mention that other conservative forces that we might look at later in the course are the spring force and the force of gravity in general. So not near the surface of the Earth. The, the, the GMM over R squared force. Okay, so in this example, we have that skier that we were talking about who um, slid down the slope, the 10-meter high slope, and was going 14 meter per second at the bottom. Actually, I should say that she was going 14 meter per second when she first got to the bottom. So in other words, over here, there. And when she gets to this level portion, the snow in contact with her skis gives rise to a coefficient of kinetic friction of 0.15. The coefficient of kinetic friction has a value for pairs of substances, right? So if you have her skis against this snow, it's 0.15. If it's somebody else's skis with, I don't know, more wax, I'm not a skier, but I imagine wax would lubricate things. It might be less than 0.15. Last time, yesterday, we were talking about uh, tires in contact with dry asphalt having one value of mu sub s, and tires in contact with wet asphalt having another one. And so coefficients of friction um, exist for pairs of substances in contact. In any case, there's a coefficient of kinetic friction equal to 0.15 that applies. And what's going to happen is the kinetic frictional force opposes the velocity, and it's going to do work that's negative because it points in the opposite direction of the velocity, which is going to slow her down and stop her, which you know, friction will cause things to come to a stop. Kinetic friction will cause things to come to a stop. And the question is, how far does she go? In other words, before she stops, which goes without saying. How far she goes is how far she goes up until the point at which she stops. All right, so in this case, energy is not conserved because you have a non-conservative force, the kinetic friction. So how am I going to solve for the distance that she goes? Well, I know one thing about about non-conservative forces. I know that the work done by non-conservative forces is the change in total energy. And the total energy of the skier at the bottom of the slope is just kinetic energy, right? She's not changing her height at all. But I can write it in general. So the non-conservative work is equal to the change in energy. The non-conservative work is the force times cosine of the angle between the force and the direction of motion times the distance traveled. Change in kinetic energy is the change in, change in energy is the change in kinetic plus potential energies. The force here is the kinetic friction, right? Which is, kinetic friction is mu k times the normal force. I'll leave it as cosine theta for now, times S, is equal to change in kinetic plus change in potential. Because if you change this, if you find the change in the sum of two things, it's the sum of the changes in the individual things. And now I need the normal force. It's level ground, so it's going to turn out that the normal force is equal to the weight. But I'm going to draw a free body diagram because it'll also help me focus on the value of the angle theta. So free body diagram, you've got the weight, normal force, and there's a kinetic frictional force. Remember, if the person is going this way, then the kinetic frictional force opposes the velocity, so it points in the other direction. And so this is Fk. And there are no other forces in the problem. So x and y directions. The sum of forces in the y direction is just Fn up minus mg because it's down. They're both completely in the y direction or minus y direction. There are no, all of them are in the vertical direction or minus the vertical direction. So the components just have magnitudes equal to the magnitudes of the vectors. There's no x component for either. And Fk has no, it's all in the minus x direction, so none of it is in the y direction. So I would add 0. And that equals ma sub y. Well, the skier is not going to fly off the snow or levitate or anything like that, or fall through the snow, hopefully. And so the acceleration is 0 because the y component of velocity doesn't change. It remains 0 as well, but the fact that it's not changing is what tells you that the y component of acceleration is 0. And so Fn minus mg is 0, Fn equals mg. Right. And you might be worried at this point, right? I've got mass here. I don't know the mass of the skier, but have faith, the mass is going to cancel. And you can see the kinetic energy is going to have a mass too, so that's how it's going to cancel. Anyway, mu k times the normal force is the weight. Now I know now, so that's mg, times cosine of the angle between the displacement and the force. Well, the kinetic friction points left, the displacement is to the right, so they're in opposite directions, which means it's 180 degrees, right? It's a full half circle. Cosine 180 degrees times s is, s is the thing I want to solve for, right? It's how far she goes before she stops. And change in kinetic energy is final kinetic energy, 1/2 mv final squared, minus initial kinetic energy, 1/2 mv initial squared. And change in potential energy, it would be mgy final minus mgy initial, but y isn't changing, right? So y final equals y initial. I'll write it out. Plus mgy final minus mgy initial. And so I look at this, I ask, is anything 0? Well, v final is 0, right? Because she moves until she stops, and so the final velocity is 0. Y final minus y initial, the height isn't changing, so y final equals y initial. So these two are the same, right? mgy final equals mgy initial, or if you, I'll factor it out and make it nice. So mu k mg, cosine 180 is minus 1 times s is equal to minus 1/2 m v initial squared plus mg y final minus y initial. But y isn't changing, so y final equals y initial, so this whole thing is 0. So I wind up with this being my equation, right? I have minus mu k mg s equals minus 1/2 mv initial squared. And I want to get s, how far she goes. So I divide by minus mu k mg on both sides. And everything cancels over here except for the s. That's why I divided by minus mu k mg. And over here, the masses cancel, the minuses cancel. And so I get v initial squared over 2 from there, mass cancels, times mu kg. Yeah, and so the mass canceled from the equation, which means we didn't need it. The how far she goes doesn't depend on her mass. And so this is equal to V initial squared was the 14 meter per second that we figured out in the last problem, times 2 mu k is given, it's the 0.15. And notice no units for kinetic friction coefficient because it's a ratio of forces, right? It's the kinetic friction coefficient is the ratio of the kinetic friction force to the normal force. And so force over force, newtons over newtons, units go away. And this is 9.8 meter per second squared for G. And if you plug that into your calculator, you come up with 66.7 newtons. 66.7 meters. It's how far she's going, so it's a distance, so it's meters. And whoop, this was squared. And just make sure I didn't goof. Yes, that's right. All right, so that is an example of how to deal with a non-conservative force. We say that the non-conservative work is the change in energy. We write the work as force times cosine theta times S, and we write the change in energy, and then we solve for whatever we're looking for. Okay. And last problem for today, it's finding the power. So what is the minimum power generated by a 35 kilogram child climbing the 170 meter Washington Monument in 10 minutes? So this minimum power business, you have to give that a little thought. Drawing pictures helps. So the initial situation is the child at rest on the ground, and here's the y-axis, and here's the 170 meters. And the final situation is the child. Now, I say that the child starts at rest because if the child's running to begin with, that running has nothing to do with climbing the monument, right? By the way, the Washington Monument, the child's not outside scaling the monument. You may know that the Washington Monument has a staircase inside. Although it was closed for a long time. I wonder if it's open now. Anyway, probably, well, I don't know. Yes, so if the child's moving at the base of the monument, that movement has nothing to do with climbing the monument. In addition, if the child is moving at the top, that motion has nothing to do with the energy needed to climb the monument. So the final situation is the child at the 170 meters at rest. So here is the child in the beginning. In the end, the child's at rest at the 170 meters. And the minimum power, I take it that the word minimum is used because there's inefficiencies in biological systems, right? We don't use our energy perfectly efficiently. So in this process of climbing, some of the energy that the child is generating is going to heat. It's being lost as heat. So I interpret this problem to be, the problem is talking about the power as the non-conservative work divided by the change in time. The non-conservative work being the work that the child expends to change their height, right, from 0 to 170 meters. And it's the minimum power because the child's expending energy, as heat. Right, so the non-conservative work is the change in total energy. The change in total energy is change in kinetic plus change in potential. The kinetic energy doesn't change, right, because the child's at rest to begin with, child's at rest at the end, at least as far as what we care about. Maybe a better way to say it is that we're not interested in the part of the non-conservative work that might go to changing the kinetic energy. So we just call that 0. And yeah, in fact, I might have wanted to start with just delta PE there, but that's fine too. And so change in potential energy is the change in mgy, because the potential energy is that of gravity near the surface of the Earth. Remember, 170 meters is still much, much less than the radius of the Earth, which is 6,380,000 meters. So a change in mgy, mg is constant, so it's just mg change in y, which is mgy final minus y initial. And so that's, I can plug in mass of the child is 35 kilograms. G is 9.8 meter per second squared. Y final minus y initial is the 170 meters, right? It's the change in height, 170 minus 0, or just 170 because that's the height of the monument. So 170 meters over delta t is 10 minutes, and I've got to convert that to seconds because I want the power in what units? Right, watts. So I want to divide out by minutes. So 1 minute is 60 seconds. And right, so if you put that into your calculator, you wind up with 97.2 watts, which is, by the way, if you look at the units, you've got seconds down here. You've got meters squared, right? Meter squared times kilograms divided by seconds squared divided by seconds. So it's kilogram meter squared per second squared, which is joules, divided by seconds. Joules divided by seconds is a watt. And notice that 97.2 watts is less than the power rating of a 100-watt light bulb. From the days when we used incandescent light bulbs. So this child climbing the Washington Monument at a fairly rapid pace. I mean, only 10 minutes to get from bottom to top. I mean, it sounds, I'd have to think, let's see. I'm going to think of a story as, a building level as, let's see, I guess 15 feet or so, something like 5 meters. So this is going to be like 34 stories in 10 minutes, which means one story in like 20 seconds, right? A bit less than 20 seconds. That seems fast. I guess. Okay, it seems fast to me because I'm not in the greatest shape. But yeah, that's climbing a bunch of stairs at a pretty good clip, I think. And yet it's less power than a 100-watt light bulb. So that's, when I started teaching this, incandescent bulbs were ubiquitous. Now they're far, most of them have been replaced, and that's a good thing. All right, I mean, why waste energy on why waste energy? Just period, right? Okay, so I suppose that there might be arguments. I mean, I'm not dismissing them entirely, but anyway, I for one am happy that we're spending less to light our homes. Okay. All right. Well, thank you very much for your time, and I hope this has been useful. And I look forward to presenting more things to you next week, because this is the end for this week. So remember the 3 graded homeworks, and you want to do the ungraded homework too. That's the best way to study for the exam. And I should mention that the Physics 1 exams tend to get more difficult as you go through the semester. At least the first exam tends to be the one that people do best on. So don't slack off. Physics 2 is the opposite. The first exam tends to be the hardest. So you have that in Physics 2. Yeah, so please, work on the ungraded homework as well as the graded, and some conceptual questions from the end of the chapter, or ends of the chapters, and thanks again for your time, and hope you have a good weekend, I guess, if I don't talk to you in office hours.